Yeah, good afternoon. Good afternoon, everybody. Welcome to today's session. So earlier we spent the most of the time in descriptive statistics. So slowly we'll get into the inferential statistics. So actually this is the one where the topics the data analytics begins with this inferential statistics. So today what we are going to discuss is like one is the continuation of the earlier class. So where we'll spend some time on normal distribution, which is one of the important distributions. Then we'll jump into the topic that is testing of hypothesis, in which we'll have so various components like random sampling, central limit theorem, and estimation. In estimation again it is finding the confidence intervals, and followed by when we do estimations there is a possibility of inviting errors. So that is nothing but here type 1 and type 2 errors, right. These are the topics that we are going to cover at max in today's class. Now one small typo here. The last session in one of the slides where we discussed the expectation of x square, in which so where actually so we have to calculate it by considering discrete random variable as well as continuous random variable, and so where we use summation if it is discrete, and actually we have to use integration, but instead of which we took I typed it as summation. So ignore this and consider this integral of x square of x dx we need to consider, right. Okay, this is like just if we recap what we discussed in the previous class with respect to probability distributions, where we had two types of two categorizations. One is discrete distributions, other one is continuous distribution. In discrete, this is what we discussed, binomial distribution, and other one is Poisson distribution. So what are the things that we need to remember with respect to binomial and Poisson distribution? One is the parameters of the corresponding distribution. Parameters means what are the parameters with respect to binomial distribution? So what are the just you try to recall like what are the parameters, because this is very important when we try to implement by using these distributions. So we have to define or declare the parameters related to the distribution. So here in this case n is one parameter, x is another parameter, and p is another, three parameters. Yeah, perfect. And Poisson, in case of Poisson distribution, lambda is the parameter. Yeah, perfect. Perfect. Yeah, mean is the parameter for the Poisson. Right, perfect. So when we go for binomial, when we go for Poisson, I think we just go through it and recall the cases where we have to go for binomial, where we have to go for Poisson, and also what is the difference between these two, or what is the relation between these two. So that is very important. So this actually is the corresponding just recap. So what is the P of x of binomial, what is P of x of Poisson, and followed by the relation between mean as well as variance. So this helps us to understand what is the distribution we can fit into a given data. Suppose we are modeling one data. Particularly this happens in some kind of mechanical applications. It happens actually when you have a data, and then you have to try to find which distribution this data follows. Okay. In such cases, one help that we'll get is we'll try to find mean, we'll try to find variance, and based on the relation between these two, we'll try to fit the corresponding distribution into the problem which we are working with. So that is mean greater than variance binomial. If mean is, just a minute, what is it? Why is clear? So why is it clear? So mean greater than variance and mean equal to variance. So mean equal to variance. This is the two things we need to remember when we recall binomial as well as Poisson distribution. Yeah, this is one of the actually one of the. Then we'll get into the next level. So this is one of the preliminary condition which helps us to look into the suitable distribution which we can fit into the data what we had. So one of the conditions. So I think you can just quickly go through the problems. Just already solution is also there. Very just for the sake of understanding. So here, so 5 car on the average 5 cars arrive at a particular day, right? And X is a random variable which takes care of the cars that arrives between the particular period. Then what is the probability that no car arrives during the period? So very simple here. And lambda equal to 4, it is clearly mentioned. And what we want to find is what is the probability that random variable X takes. So here how we calculate lambda is it is given actually. So they have to give the parameter value, or sometimes if lambda if they won't provide, then we have to look for M and P. If these two are available and if we are going to fit or try to fit Poisson distribution, if lambda is not available, then we'll try to use this lambda equal to NP. So we need to have N as well as P. N is the number of trays and P is probability of success, where N is very large and P is small. How to identify whether it is binomial or Poisson? In general, very easy to identify Poisson if N is very large and P is very small. That is the best criteria to identify whether we can go ahead with Poisson distribution or not. It is very simple. Suppose if you had N equal to 100, suppose N equal to 100, let's suppose. And we want to find the probability where X takes a value greater than 10. Probability where the random variable X takes a value greater than 10, suppose. Then if you see how large you can understand here. Suppose it is X 10 now, 10, 11, 12, 13, 14 and so on up to 100 we have to do it. Right? So that is N is very large. Then not only this, we will see the corresponding P also. P should be nearer to 0, right? And one more condition is we can calculate N into P, and it is almost behaves like a constant. Then it follows Poisson distribution. But for us, mostly we go for binomial distribution and normal distribution. So as far as the applications what we had in various courses mostly confined with respect to binomial and normal distribution. Is it clear? Okay. So next is like a similar problem. There is almost similar. So why did what is the definition for lambda? Lambda is nothing but the parameter which is the mean as well as variance. So mean, this is the parameter of the distribution which they need to provide actually. And we already know lambda is nothing but mean equal to variance and also the parameter, and it is a Poisson distribution. So we need not do anything with respect to lambda. One is they need to provide lambda, that is if they provide mean, then it is nothing but the lambda, that is one. sometimes what they do is without mentioning all these things, simply they say they mention or they take a situation where it is the rarest of the rare event happens. Rarest of the rare event happens means n is very large and p is very small. Large in the sense, n is maybe thousand, like no actually no parameter, no what we call as a boundary for us to say this has to be the larger n. That's we have to see what is n and what is p correspondingly. We have to identify. We have to calculate lambda. Once lambda is there, very simple to do the calculations. Which one? This one, e power minus 5. That if you see here, lambda equal to 5, and we want to find it no car wash. That means x equal to 0. Then e power minus lambda, that is 5. Lambda power x, 5 power 0, 0 factorial. 0 factorial equal to 1. Therefore, 5 power 0 is 1. Therefore, e power minus 5 comes into picture. So y0 means here you see what is the probability that no car arrives during the period. What is x here? What is the random variable? Random variable x is the number of cars that arrives between 10 and 11 am. That is the random variable. But x equal to 0 means that is no car arrived. X equal to 1 means 1 car arrived. X equal to 2 means 2 cars arrived. So what are the corresponding probabilities? So that means yeah, almost e power minus 5 if we calculate, then accordingly we can comment on like, so depending on the probability, then we can say there is no possibility that this situation happens. If it is suppose 0.8, suppose if the probability is 0.8, then we comment saying that the probability is very high, that means this event happens. That's why in general, in analytics kind of courses or in analytics kind of applications, not only getting the values, calculations and output, the interpretation is very much important. Okay? So suppose in this case we got some output probability as 0.8. What is this 0 point stands for? Based on the 0 point, what is the comment that we can say? So that is very important in the data science analytics kind of applications if we take. So lambda probability is very high, then means the event happens with maximum probability. If it is almost less, that is 0.2, 0 points, that means the possibility or probability of happening of this event is very less. That means we say we can rule out that this is not going to happen. So that interpretation is very important in most of the courses which are in and around data science related stuff. Now similar kind of some another random variable where lambda is I think this is again typo here. This lambda equal to 5 only. Car wash is not same. Some random variable is given, lambda is given, and they asked us to find out what is the probability that it lies between 48 and 50. Lambda equal to NP is nothing but that is what we discussed in the last session. Actually, in one case, the binomial distribution becomes Poisson distribution. That is when n is very large and p is very small. Then if we calculate mean of the binomial distribution, that is n into p, it almost behaves like a constant. There's very less variation. So that's why that NP, which is a mean, is denoted by lambda here, which is called as mean as well as variance as well as parameter of the Poisson distribution. But it is very rare. The separate like some other applications. Suppose if you take queuing theory kind of applications, this is one of the important distributions we need to apply. The n is very large and p is very less. N is very large and p is very small. Then we have to use Poisson distribution. very just I want to touch that concept also. Now next is one of the important concept, that is normal distribution. So what is this normal distribution? So here, as we discussed, so this random variable is either discrete or continuous. Suppose if you take continuous, that is which takes values in an interval, then we say it is a continuous random variable. In case of continuous random variable, if you remember, we use we denote a function f of x, right, which is called as probability density function. If a random variable which is continuous and which takes values between -infinity to infinity, and having this f of x, which is defined by this lengthy expression 1 by sigma into root 2 pi e power minus x minus mu whole square by 2 sigma square. Then we say it follows normal distribution. As mentioned here, it is many names are there. Some people call it as Gaussian distribution also. We call this as normal distribution. Maybe when you go with mixture models in machine learning, you will be using this term Gaussian distribution regularly. Gaussian distribution, Gaussian curve. And next one, suppose if we plot this, it takes all the values in the interval -infinity to infinity. And if I take all the, if I give x equal to positive values, negative values, almost all the values, and if I plot, then it looks like this curve, which I think most of you are, this is the most favorite curve for you, that is bell curve. So the bell curve is this actually, bell curve, normal curve, or Gaussian curve, which is this. Let's see how to use it. Now if you see here what happens, you will have the highest peak followed by tiles, etc. This is, I think, you maybe you are using in your appraisals, etc. In appraisals, mostly we try to fit it into a bell curve, and accordingly we will see who can be given higher rating, who can be given lower rating, etc. Now I think slowly that we are coming out from the bell curve, but still it is popular curve. Now we'll get into. Suppose if we want to find out, just don't be scared of this integral kind of thing. Very simple, just to understand the concept. Just I'm explaining. Suppose we want to find the probability that random variable x lies between x1 and x2. So suppose if I say this is 20 and this is 25, right? Suppose we want to find out the probability where x takes values between 20 and 25, which is a closed interval. Then we know if it is a discrete random variable, what we need to do is p of 20 plus p of 21 plus p of 22 and so on up to p of 25. Then depending on the distribution, we go for corresponding p of x and we do the calculations, right? If n c x, then what is n, what is c, at every point we'll find the probability, then we calculate. But here, because it is a continuous random variable, we can't do the summation, right? Instead, what we have to do, we have to go for integration, right? Integral of x1 x2 f of x dx. Right? There summation p of x, here it is integral x1 to x2 f of x dx. Then integral x1 x2, what is p of x here? The same like we'll copy here. 1 by sigma del expression whatever is there. 1 by sigma root 2 by e power minus of x minus mu whole square by 2 sigma square. right? This is into dx. This we have scaled out this integration actually. It's very this now actual procedure is, I think you might all observed, as I think you recall the problems which we did earlier, integral of some 2 to 3 x dx. You remember the problems we tried. How we did integral of 2 to 3 x dx? We did the integration, then x square by 2, right? Then we have to substitute the limits, right? I hope that we recall that. Now also what we have to do is we have to do first we have to evaluate this integral. It is something x dx. Now we have to go for x square. Yeah, perfect. X power n. Like this, we have to evaluate the integral. After the integral, suppose some value we got. Like x power n integration is x power n plus 1 by n plus 1. Integration is over. Right? X cubed by 3. After that, what we do? We substitute upper limit here minus. Again, we substitute lower limit here. If you remember, this is what we tried. Okay. Whenever integration is there with limits, this is the procedure. But the problem here is there is a problem with respect to this. This is a very complex integral which we cannot evaluate. So we are very lucky actually. We are very lucky and happy that we cannot evaluate this integral. If we can't do the integration, then what to do? Anyhow, we want some output from this. So then what we do is we do some substitutions and we convert this integral. If you are able to follow it, fine. Otherwise, just listen and forget about it. Right? If you follow this, excellent. Otherwise, also no issue. Now, if you see here, this is a constant, right? This is a constant. Keep it out. Then what we do is we do substitution x minus mu by sigma equal to some z. This is the substitution we are doing for the integration. X minus mu by sigma equal to z. This we need to remember. Now x minus mu equal to sigma into z. Then I differentiate this with respect differentiate both sides. Then what we get is derivative of x is dx and derivative of z is dz, where sigma is a constant, it remains as it is. Derivative of mu is a constant whose derivative is 0. So that means after the substitution, this dx becomes sigma dz. We substitute here now 1 by sigma root 2 pi e power. Now here this is z, right? So z square by 2 with minus, and dx is sigma dz. Okay. I hope that's clear. Otherwise, also no issue. Just try to follow. If you are able to understand very clearly, fine. Otherwise, just forget about it. And we had a procedure to follow. Dx equal to sigma dz. Now simply x minus mu. If we go do the cross multiplication, then what we get is x minus mu equal to sigma dz, where mu is a constant. Addition or subtraction, you had a constant. Then sigma dz. Then if we differentiate this, here both are variables. X is a variable, z is also a variable. Then derivative of x is dx, derivative of constant is 0, and sigma is a constant, it's a multiplication, therefore it stands there. And derivative of z is dz. Derivative is nothing but, in a simple sense, which talks about the change that happens in that variable, which is denoted by dx in a simple sense. Therefore, if we differentiate x, then we get dx. If we differentiate z, we get dz. Okay. Now we substitute here. And one more observation you might have had. Now what we are doing is we are replacing x in terms of z. Then obviously this x1 becomes some other value, right? Suppose it is z1. Suppose x1 is becoming z1. And similarly x2 is becoming z2. Then we'll go to the next one. This is what we get. So this is what we get. Now what we expect is, suppose if someone gives the integral value, simply we replace upper limit minus lower limit. Suppose if someone says this integral value is f of z, how that depends on the who is giving that value. Suppose this is f of z. What is this f of z? The value of the integral by using some methods that he knows. Right? We are least bothered about what he is doing. Our concern is what is the outcome, that is f of z. Once we are ready with f of z, very simple, right? Simply we have to replace upper limit. Therefore, it is f of z minus f of z. So this is how the normal distribution is. The probabilities in the normal distribution is calculated. Okay. So don't be scared of the math kind of derivative. Simply, what is the take here is integral x1 to x2 f of x dx is the one which we have to evaluate, which we cannot do. Then somebody will help us with some f of z. What is z here is z is x minus mu by sigma. Once f of z is available, we replace upper limit, that is z2 minus z1. That gives the probabilities that we are looking for. So generally integration is some kind of problem most of the time.